My problem. Okay. So my problem is the following: is a short work with Muriel Livernet, and you consider two types of algebras, and you have a functor from S algebras to T algebras over the forgetful functor. So it means that the functor, I mean, the underlying vector space are the same. Okay, you lost some structure from is to go to T, but on the same vector space, and you consider a left adjoint functor. So it is very easy to do it. You may just take the free S algebra and then take some quotient, and you get a left adjoint. And the question is, if you have a T algebra, when can you say that this T algebra, I mean, you have a canonical map from A into its enveloping algebra when this map is injective? The classical situation is when you go from associative algebras to Lie algebras, but if you look, for instance, to the proof of Quillen, it's quite complicated to see that the Lie algebra, I mean, the Lie algebra injects into the universal enveloping algebra, but to prove it is now you have a lot of bases and so on, but it's not very easy to do. So this point of view is developing a paper from Mikhail Lefa and Shestakov, but we take a quite different point of view. So I like this presentation of the problem, and this is due to Dotsenko and Tamarov. So you consider in the functors, okay, you take a category and you look of monads in the category of and the functors of C with the composition. So they go to quite a strong theorem that says that, let me say, if you have a natural transformations from M to N, then this data has the Poincaré-Birkhoff bit property if the action of M on N is free. Let me point out that when you have, okay, we are going to look at M on an N as type of algebras, so they are operads, and operads are just monads in the category of endofunctors of the category of vector spaces, and you have to restrict yourself to the category of analytics endofunctors. But it works, and in this case, they show in particular what they prove in their proof. They show that you have that N must be the composition of M with another analytic endofunctors, okay, X, which is not easy to compute. This is the problem. And so let me point out that in this case, for me, M, I mean, is Lie, and N is associative, because when you have from M to N, you have from the category of N algebras into the category of M algebras. And we have many problems. Normally, what you are thinking about is that X encodes the coalgebra structure you have. I mean, somehow you're saying, okay, objects, you have free objects for the N are exactly some kind of bialgebras where X provides the structure of coalgebra and M provides the structure of algebra. And normally in your examples, in X you have something, a functor at least in the category of associative algebras, and M has a functor in the category of Lie algebras, so from M algebras to Lie algebras. So I'll try to explain the example we needed to see, and this is the following one when we have M to be pre-Lie algebras and N to be Dendriform algebras. So they apply and they show that this data has the Poincaré-Birkhoff property. So it was an open problem from a number of years, not very, well, not very important maybe, but an open problem. So the I'm trying, no, I cannot. Just, so let me describe a bit. A dendriform algebra is just an associative algebra having another product which is not associative and which verifies some relations and with the associative product, and this is the description. And a Prelli algebra is just you have only one product, and the associator is not zero, but is antisymmetric. I put left here, so I don't know. So can you see my pointer? Yeah, okay.
Yeah.
So it's antisymmetric in the two last variables. Okay, if you want to write this, you have the relation with x and y, but it's more or less the same. So in particular, associative algebras are an example of Prelli algebras. And we have functors, I mean, from dendriform algebras into Prelli algebras and from Prelli into Lie. I mean, if you antisymmetrize the Prelli product, you get well, something which is antisymmetric, but it satisfies the Jacobi relations. And if you are working on a dendriform algebra, then you have this formula and you get a Prelli product, a left Prelli product. Okay, and now I need a bit more. I need some kind of generalization of Prelli algebras. So now you have a Prelli algebra, okay? But a brace algebra is you have an infinity of products, and M11 is a Prelli product, but you have a whole family and you get a deformation of the shuffle product on B. So you need you have B. If B is a brace algebra, your brace structure is exactly a formal deformation of the shuffle product. So the formula is a bit, you just have to break Y in several pieces and make all possible combinations and you get the formula. So now you have from brace into Prelli is quite easy because you just keep the first product M11 and it is Prelli. And from dendriform you may get also a brace structure. So the first, the Prelli structure is this one, which is, okay, the previous one. And you may define this, the rest of the deformation like that. So you just, it's a kind of operator which is quite easy to work with. And what we have, but not from, I mean, it's a quite old result now, that dendriform, I mean, X in this case is the operad of associative algebra. So like an S module is just the regular representation of the symmetric group on each degree. And here you really have, I mean, you really have a Hopf algebra. You may prove that any dendriform free object is a Hopf algebra, and this is your co-associative coproduct, and then you have brace, okay? But inside, okay, you have, and from here you have the Lie algebra. I mean, the Lie algebra is just this, a small piece of the information you have on brace, but you get everything. So our problem just was to work not with dent, but with a more generalized algebras, I mean larger algebras. I may say that all my examples are what you call combinatorial Hopf algebras. So you have, they are not by the algebras, the Hopf algebras may not be graded, but the underlying vector space are graded and have fixed bases on each degree. And normally the bases are partially ordered sets. So it's like permutations with the Wick-Bruat order or trees with the Tamari order, and you may, and some generalizations of the Wick-Bruat order, which are called facial orders and were defined in recent works by essentially Vincent Pilot and Vivian Pons and Christophe Holbeck for Cox-Ritter arrangements and so on. So we have a very, very particular, they are infinite, but they are really quite easy to manipulate. They are combinatorial. It's not very, very complicated. So what we wanted to study first are operads related to lattice paths. So what I consider a lattice path is something that is a path, okay, which does not cross the x-axis, and you have up steps of any length. I mean, I have fixed m, so to begin, I may suppose that up steps are of length n, and down steps are of length 1. Okay, so I want to study all the paths from, you have to begin at the x-axis to finish also at the x-axis, and then you have just a walk like that, which never goes down the x-axis. And we want to describe, I mean, operads which you can build on this kind of combinatorial object. And the idea is the following. You may number, I mean, you have to number, I put it down, your upper steps in order. So this is 1, this is 2, this is 3, this is 4, and 5, and so on. 7 and 8, okay? And what you are doing, if you have a down step, you go from the middle of your down step, you take a line, and you number this step by the upper step, which is just the first one you find when you do this line, okay? And there's only one way to do that, so you get a canonical way to number all the down steps. And if you read, I mean, if you read only down steps from left to right, you have a word. And this is what is called multi-permutation. So you get a lot of examples of this type of algebras. And it's moving. So how can you describe this lattice path? Of course, you may, I mean, if you fix the length of the upper steps, then you get n+1 binary products. If you may consider with upper step of no matter what. Sorry, I have a question. Oh, I don't know. So I have, you may do that, and you may, I mean, you will have some filter operand with an infinite number of binary operations, but the procedure is more or less the same thing. I mean, and you will recover in the filter, in the associated graded operand, all these operand dic m, but it's just, and they are defined by these products and quite easy relation. So you have this star, I put it outside, and they satisfy some relation. I mean, they are not, they may be a bit complicated, but not too much. So to work, they are quite easy to manipulate. And the free objects are just color. Now you have to color by your elements x, y, the upper steps, and you get a large Hopf algebras on dic path. What happens, you have many examples, because whenever you have some dendriform algebra, like the Malvenue-Reutenauer Hopf algebra, or the planar trees Hopf algebra, or the backwards Hopf algebra, and so on, what describes this dic m is just you have a poset. I mean, on each degree you have a poset and of these algebras, and then the operations are given by intervals. I mean, when you study the dendriform structures. So if you consider the m simplices for these posets, then dic m, you have a dic m algebra. So dic m acts on all these examples. You have a dendriform algebra with this condition of the order, and the M simplices of these objects are just examples of the M algebra. So we have a lot of examples. Okay. So, and of course, the M, you have M different ways to construct a dendriform algebra. So a star is always the sum. And then for each E, so you have exactly E goes from 1 to M minus 1, let me say. From 0, I'm sorry, from N minus 1. And you get M possible dendriform algebras. What we wanted is, okay, so you may translate, and I will not give the all descriptions, but you have brace M is essentially, you have a brace algebra and you add these operations from 1 to M minus 1. And the relations are a bit complicated, but you can do the analog of embrace algebras. And then, okay, you want to study that. You want to show that this pair has the Poincaré-Birkhoff property, and you want to describe X. I mean, this is our main problem. And of course, you have also an M version of Prelli. And in this case, we know everything. And again, we have dic M, but we have it. Okay. It's just as composed with brace M. So again, you have there, you have real bialgebras. And here, well, we don't know. And it will, I mean, we have very, very few possibility to recover Hopf algebras, essentially. I mean, X is a bit more complicated. So the problem really is to prove that this pair has the Poincaré-Birkhoff property. And essentially what we wanted is to use for M equals 1, you get Dendriform and brace, the original ones, and we know the result. And we wanted to see the way to generalize it. And this is not, I mean, it requires a bit of work, but it's just rewriting the way you consider Dendriform algebras. And somehow it explains why you cannot recover, at least, I mean, you cannot recover an associative coproduct and I mean, dic M or Dendriform M as an associative coproduct on Prelli algebras. So we rewrite, I mean, the presentation is this one, and this is equivalent. And here you put just your Prelli product. And what you can see is that the idea, more or less, is this product is not associative, but you may make some, I mean, you may have some standard presentation where you consider, and I put it from N objects, you may consider a standard way to rewrite them, and you get this type of things. So you pile on the left to that, and your coproduct will be just to treat this element and x1 tensor x2 tensor xn minus 1. So well, I'm ready. Okay. So there you have your coproduct, but you have a bit problem and you can see it. So you want to write down all your elements in such a way that sorry, I have some connection problem, I think. So in such a way that you may write, I mean, any element of in your Dendriform algebra may be written like that, and the x1 are constructed only with your Prelli product. And you see that it's not possible.
Maria, your presentation is not sharing anymore.
Ah, sorry. Sorry. Okay. Yeah, I have these problems. Okay. Ah, dice que lo inhabilitaste.
Aju?
No, it's the other host, possibly. It's because of the other room. I think the other person, maybe.
Gastón, ¿puedes ayudarnos? Porque
I
ya no soy...
will go. Yes, I will go and settle that. Okay. Just wait 5 seconds. I will go and settle that.
Yeah, sorry for this. It's that there is a session, all the sessions like have two options of blocks, and one ends at around 4 p.m. Argentinian time and the other starts, and there are some share rooms for some reason. And so the last talk of one session and the first of the other has this kind of problems. I think we didn't know this before, so sorry for this. This was kind of last minute.
I thought it was mine, my Wi-Fi, but no. Okay. So
About that.
So the detail is a very, very stupid point, but we had not remarked it before, then that when you look at the properties of your Prelli product, you get this kind of things. I mean, this element and this one, and you cannot take off, I mean, change and take off your left product. And so the only way to have this standard writing system for any Dendriform algebra is just to consider this element. And this element is precisely what we call the M12 of X, Y, and Z. So if you want to put an associative product, you just need to, and then you have X, sorry, this is, I'm sorry, I'm doing, this is Z, okay, as X, Z, X, Y, and then you get it. So if you want to have an associative product, you have to put this in some, I mean, to consider this element, you have to add the two braces. And then when you studied, clearly, when you study the relationship of your product left with this, and the Prelli product with these braces, you shall need to add up M13 and so on. So this is the reason why when you want to study Hopf algebra, you just need to put not only Prelli, but all the brace structure. So, okay, I have no more. So this is more or less what I explained there. Well, so it proves that. Okay, so using these constructions, we were able to prove clearly without studying freedom and so on in the category of monads that you have really a Poincaré-Birkhoff-Bit property in this case, and we may compute I mean, we have a theory where we have a brace structure plus some products, and this is on the premise. And this somehow, I don't know if I put, no, okay. This is more or less the examples I wanted to give. Why? Because we have many problems, okay, in this story. Here, okay, we have for all these operads defined on a lattice path, we have these constructions, we have a family of Hopf algebras, and we know we have some kind of a Cartier-Miller-Null theorem, which is obtained just with some calculation, but using the case of Dendriform and brace algebras. But we have another, and this is okay. We have another case which we are trying to do now, is replace really by Lie admissible. So a Lie admissible algebra is an algebra equipped with a binary product, and that when you anti-symmetrize it, you get it verifies the Jacobi identity, and you have a Lie algebra. And in this case, we know how to compute. I mean, we have some. We have some theories to make the enveloping of Lie admissible, and we have, again, when we compute the primitive, we get much larger structures. We have infinite families of products, and also, well, and this is more or less a problem related our more simple examples on real Hopf algebras. Normally, our question is related to the following. Suppose you have a theory, and suppose you can, on the free objects, you can always describe some coalgebra structure. And so you have, you may describe completely by the primitive elements of your theory. I mean, you have always a theory which describes your primitive elements if you work more or less correctly. And so you want to relate your your operad, your algebraic theory related to primitive, to your algebraic theory related to enveloping algebras, and prove some kind of equivalence of categories modulo your coproducts. And what happens, and this is the problem, if you say, okay, I have an algebra, I have a type of algebra, so I have certain operations and I have certain relations between these operations. What can I say on the primitive? And if I know, and I take off some relations, or I take off some operations, what will I find like a theory? I mean, what it will give me when I change that. And this is a quite complicated problem as we have some examples more or less, but not general results. I mean, there are a lot of people who have tried to work on, and it's not really easy. Well, and I think it's okay for me. I mean, thank you very much for being so patient, and okay, it's all right.